how does the world really work? Science has made spectacular progress, assuming that particles and forces describe all that exists. This principle is called reductionism, which means that every physical thing can be explained, down deep, in terms of physics. But take ordinary stuff. Study all its parts. What do you get? Not what you expect. What's going on? Simple ignorance or something more? It seems a mystery, and it's called emergence. Somehow, the underlying laws of nature, as we know them, cannot account for the world. So can emergence explain reality? I'm Robert Lawrence Kuhn, and Closer to Truth is my journey to find out. I start at Stanford University with Robert Laughlin, a Nobel laureate in physics. I hear Bob rejects the traditional approach that the way to understand the world is to break it down into little pieces. Bob's world is more than parts. We meet in his home. Bob, I really want to understand what's fundamental, and the history of science tells us that we have to look at smaller and smaller things. You have talked about a transformation of this traditional worldview, that instead of looking at smaller and smaller stuff, we now have to look at how nature organizes itself. What does that mean?
Let's imagine you're on an airplane at 40,000 feet eating peanuts. Now you know that that plane won't disintegrate. That's why you're willing to stake your life on it. It's a law. Now where did this law come from? Well, you might say it comes from the atoms, but it doesn't. The reason you know this is because when you take the pieces of metal apart to see where the rigidity comes from, it vanishes away the way the meaning of a pointillist painting does when you get very, very close to it. In other words, rigidity is something that atoms do together. It's the togetherness of them that makes rigidity.
Now, the term that has been used is the concept of emergence. How do you define emergence?
Namely, a law that means relationships among measured things, that's always true, that comes about because of organization.
Well, the most common one are the phases of water: ice, water, water vapor. How does the concept of phases give us a window into what emergence really is?
Of course, the phase transitions of water are very familiar to everybody because you have ice in your refrigerator and you have water coming out of your tap. They're not particularly unique. Phase transitions happen all over the place in nature. Now, the transition is a transition between what? It's between two forms of the matter that have different rules of behavior at the longest scales. Now, at the shortest scales, they don't have different rules of behavior. In fact, when you do X-ray measurements on a little piece of water, a piece of ice, you can't tell them apart. Okay? The rigidity of the ice only becomes clearer and clearer and clearer as you step back from it. Lots of things in the natural world have this property that you learn less about them by taking them apart. If you want to know whether your airplane is going to come apart, then you look at these big scale things, these emergent things, because that's what matters. On the other hand, if you want to control rust, that has to do with things on a very small scale, chemistry, and so you ask a different set of questions for that. The point is, we don't have a monolithic world. We have a world that's populated with things you measure, cause and effect relationships between things that are always true. And some of them are socialist in nature, they're collective in nature, and others are more fundamental.
It depends, Bob says, on what you want to know. About some things, you learn less by taking them apart. The whole is more than the sum of all the parts. Do all scientists think this way? Not Peter Atkins, a world-renowned chemist at Oxford University. Peter is a tough-minded reductionist and proud of it. Well, maybe not quite that either. Best I should hear Peter tell it. Peter, if we look at what we find in the world, elements, water, at the extreme level consciousness, all of these things are made of more fundamental things. And yet if you look at the properties of those fundamental things, there seems no possible way to combine those to yield these emergent kinds of characteristics.
That's defeatism, isn't it, when you say, why there seems to be no way. That's the whole point of we scientists. Although we might be reductionists and sort of stripping away matter down to its fundamentals, we're actually assemblists. We really do try to go in the opposite direction to understand how properties can emerge from the simpler entities.
Well, if today you had every characteristic of hydrogen gas in one set of books and oxygen gas in another set of books, would you be able to even begin to describe the properties of ice?
Yeah, you bet I would. And water, that most amazing stuff. I can reverse engineer water, and I think, reverse, well, let's take a property of water, wetness. First of all, I know that from the properties of hydrogen and oxygen that they will form molecules H2O. Okay. I know the shape of the water molecule, sort of angular shape, that sort of thing. Well, these little patches that really is like scouts that go out blazing a trail, really. They can sort of wriggle around and find a positive patch can find a negative patch and so on, move towards it and so on. So I think that water can spread across the appropriate surface. So I think I can predict quite a lot of the properties of water. I see no real problem with, for example, the structure of DNA. I mean, which follows almost logically from the structure of the nucleic acids itself. And once you've got to that point, you can begin to understand that it's an encoding device for inheritance. Then I think you could make a good stab at, in due course. We can't predict protein structures yet.
It's fiendishly complicated.
Fiendishly complicated, but the fiend is not going to defeat us. We're going to get there. I mean, that's the whole point about science, is this driving optimism that it has. You don't go into science if you think you won't find the answers.
I struggle with this idea that there are different levels in the organization of reality, where the kinds of explanations that we use at some atomic level, at atomic level, molecular, and then when you get to biological systems, and as you've said, consciousness, seem to be different. But if we can begin to explain those jumps, then it may be much more of a continuum that appears to us today.
Yeah, well, I'm sure it is a continuum. I think it does have different types of explanation, but they show an evolutionary sequence, really. And we wouldn't dream of bringing sociology to bear on the structure of the atom. but I think in the opposite direction, we could bring the structure of the atom to bear on sociology.
But it only goes one direction.
I think it's true to say it goes only in one direction. But I think the point to remember is that science is still very young, and we're still learning, and we're assembling. We're cautious revolutionaries, basically. That we're assembling our forces by stealth. You could almost say that we're learning We're doing our scales, our 5-finger exercises and so on. At some point, we've got to bring our 5-finger exercises together to get a tune. And then we've got to get a tune, and then we've got to orchestrate it to get a symphony and so on. Science is an optimistic pursuit. And as soon as you start saying, we'll never explain that, you're no longer a scientist, in my view. I think you become a philosopher then.
You seem to say that in a very derogatory way.
To Peter, scientists are assemblists. When you understand the pieces really well, you understand the whole. There's nothing ultimately mysterious about whole things. Emergence, Peter says, can be an excuse for lack of knowledge. Scientists should be optimists, confident in the explanatory power of science. I love the sharpness, the antagonism of the opposing views. Either emergence is key, or emergence is excuse. How would a biologist think about emergence? Francisco Ayala is a renowned evolutionary biologist at the University of California, Irvine, where he is also professor of philosophy. Francisco is entranced by biological organisms. Suppose we learn all possible physics. Would we then know all that living creatures do?
Francisco, can you reduce biology to physics, or must there be something emergent, something special, when you have living systems?
Let me use an analogy. Think of a house made of bricks. The laws by which the bricks are made are not the same laws by which the house is made. You cannot have a house without bricks. Moreover, if you remove all the bricks, there is no house left. But the house is reality, a different reality from the bricks. So going off the comparison between biology and physics, between living organisms and their components, we are made up of atoms and molecules. Living organisms obey the laws of physics and chemistry, but the laws of biology are completely different. They transcend, they emerge, if you wish. You have to study the life processes at their own level. It's always good and helpful to go to understand the underlying levels. But of course, most of the underlying levels in life process are still life processes. Only at the very bottom, they are the laws of physics and chemistry, which are relevant.
Right.
But what we want to learn about organisms is not the laws of physics or chemistry.
But there are some people who are reductionist, radical reductionists, who would believe that at some point in the future, I mean a million years, that you can, from the fundamental laws of physics, known perfectly, you can derive upwards so that you can explain biology and then psychology and consciousness.
Well, there's an act of faith, and almost anything that I know about science goes against it. Tell an architect that by keep studying more and more about bricks, the laws of how to design a house are going to become clear. Sometimes people who claim that physics can explain biology or that atoms and molecules can explain organisms are confusing two different issues: the ontological question and the epistemological question. Ontology has to do with makeup, constitution. The epistemology has to do with knowledge, how we know about things. So in the house, you have the bricks and you have the house. If you remove the bricks, nothing is left. There's the ontological question. In a human being or in any other organism, you have the atoms and the molecules. If you remove them, nothing is left. But now if I want to know about the house, I go and study the science by architects, not bricklayers. Studying the bricks and knowing lots about bricks by themselves. I mean, it's nice to know that the properties of the atoms, the laws of physics and chemistry, but what I want to know about organisms are completely different things. That's the epistemological question, the question about what do I know and how do I know? And for that, I have to study the organisms in themselves. I'm not going to learn much about fish.
Studying everything about bricks will never explain very much about houses. Each level of organization has its own laws. And meaningful understanding comes only by studying each and every level on its own terms. Another way to view the world is to ask about complexity. How do complex things form from simple elements? I go to Boston to ask one of the world's most innovative thinkers. Stephen Wolfram is a physicist who created radically new software for technical computing. He explored the origins of complex systems in his controversial book, A New Kind of Science. Stephen seeks to discover the secrets of nature by uncovering some very simple, very special rules.
Well, I think it's in a sense kind of humiliating for us as humans that if we're presented, let's say, with two objects and we're told one of them is from nature, one of them is something that we as humans have created, that it's a pretty good guess that the one that looks simpler will be the one that we as humans have created. And yet, with our whole sort of history of civilization and so on, somehow we haven't managed to capture the secret that nature seems to have that lets it, apparently quite effortlessly, create all the kind of complexity that we see. So one thing I've been very interested in is to try and sort of home in on what that secret that nature has is. It's kind of a very basic mystery in science. I thought 25 years ago when I started really thinking seriously about this kind of thing that with all of the fancy physics and mathematics and so on that I knew that this kind of basic mystery of science will be easy to crack. What I kind of realized is that we have to sort of start thinking about what are all the possible rules that nature might conceivably use to do what it does. They might not happen to be the rules that we as humans have set up in our mathematics and in the development of our science. So in modern times, we have kind of a good foundation to think about all possible rules. We have computers and computer programs, and we can kind of imagine looking at sort of all the possible programs, each one corresponding to a different rule for how things get made. And we can ask the question, in the space of all possible computer programs, what's out there and how does it compare with what we see in nature? My first assumption was that when the programs I was looking at were simple, then their behavior would somehow be correspondingly simple. If one wanted to make something complicated, that it would necessarily be the case that one had to sort of put something complicated in, that one couldn't get complexity out with nothing put in. So I was fairly amazed when I actually did the experiment and found that some of the programs that I looked at were very simple, did very simple things, but if you just start enumerating possible programs, by the time you're at, let's say, the 30th program, that happens to be one that I particularly like. You can number these programs. This is Rule 30. Yeah. You suddenly see a situation where you can start off from a very simple rule that you can specify in just a few bits of information. You say, let's start the thing off from, let's say, one black cell in the kind of ways that the pictures are made. And suddenly you see that out of this very simple rule, very simple starting condition, you get this pattern of great complexity. It's the single most remarkable thing that I've ever seen. So in a sense, the answer to the question of where does the complexity of nature come from is nature is sampling the possible rules in the computational universe, and it's then just a matter of basic science that out of these possible rules in the computational universe, a fair fraction have this feature that they produce complexity even from very simple underlying rules.
Stephen has shown how simple rules can generate complex patterns in surprising and elegant ways. He claims that for understanding reality, rules may work better than mathematics. But can emergence give clues as to the basic structure and perhaps deep meaning of the universe? Many scientists dismiss such a notion. As for me, I cannot help but wonder. To Philip Clayton, a philosopher and theologian specializing in science and religion, emergence is a new way of watching the world. Philip somehow sees emergence as a third way between pure science and fundamentalist religion. Can this make sense? If so, this is wild new territory. We meet at Harvard Divinity School.
Emergence is the realization, I would say, that the natural world is composed of multiple levels, that as systems get more complex, they don't just continuously evolve into something new, but at some point in complexity, you get a new type of phenomenon, a new type of dynamic. And that needs to be explained by scientists in a different way than that of the lower level.
So what does that mean? What follows from that?
It means that the biological world is much more interesting than we thought it was. We're not little
You're saying
machines.
in principle you can't do it? I mean, if you knew everything in every possible way, if you were God, so to speak, and you knew every particle and force possible, you would still not be able to predict?
That even God would have to do some looking. That's true. We really are responsive organisms to our environment. And so even the omniscient scientist, God qua scientist, is going to have to look at the interactions between these beings. And in a few cases, you have a virtual reduction of the one to the other, say physical chemistry to physics. Those are the tightest relationships that exist anywhere. But it's an ideology, I suggest, to take that one instant and then to try to say that, well, that is how the cells of a chimpanzee and the behavior of a chimpanzee are related.
You've talked about strong emergence and weak emergence. What's the difference?
Weak emergence is the kind of emergence we generally find in physics. That's the case where the broader system, say in solid state physics, some particular massive body, constrains the behavior of the parts. But strong emergence adds another dimension. Let's say in the case of an organism, it would be silly to say that the behaviors of the organism are just a passive constraint and all the work is done at the chemical level. An organism is an entity that's engaged in this interaction with its environment, in the struggle for survival. And that makes it an active agent. Strong emergence then says that this active agent is a causal force which is causing its parts to behave in a particular way. Evolution consists of a series of these recursive systems, and in each case, a complex system engages in dynamics that moves the parts around. And in the case of living systems, the most natural way to speak is to say that the organism is the active agent. It's downward causation, the fact that an emergent organism exercises causal influence on its parts.
That one is the troubling one.
Yeah.
To say downward causation means that the sum of the parts is influencing the parts themselves in some recursive manner?
That's exactly right. At each level, we have new information from the empirical world. We seek connections, but we don't begin with the dogmatic assertion that we'll be able to tell the story top to bottom in one unbroken narrative.
There is something about whole entities that is more than the sum of their parts. Emergence is a radical view of how the world works. Unique laws operating at each level of reality, which are not reducible to the laws of lower levels of reality. This would be remarkable, forcing science to think anew. Emergence claim, disputed by some, is that reductionism does not always work. Biology in particular cannot be explained entirely by physics. Emergence may take two forms. Weak emergence, when unexpected properties appear in whole entities that could not obtain by simply combining the properties of their parts. Strong emergence, Whole entities have causal powers that affect their parts. Causal powers that exceed the sum of the powers of the parts. Downward causation is real. Downward causation, that would shock. Emergence shakes our worldview. But is it closer to truth?
For complete interviews and for further information, please visit closertotruth.com.